So we're off to greener pastures. Yeah, we're off to talk about something other than the addition of an acid, an HCl or an HBr. And I told you in this video, we're going to focus on water. And then I left you with a question. And I said, what? Water? An alkene reacting with water? Well, an alkene is typically nonpolar and water is polar. An alkene is typically soluble in other components that are very similar to it, and these would be organic solvents. Alkenes are not soluble in water, so how do they react? Well, I'm going to make it easy. An alkene and water will come together, and they form a product that we call no reaction. That's right. Nothing's going to happen here. Zip. Doodah. Go have a grand old day. Alkenes will not react with water. If it's just water only, these are very easy questions to answer, and you're going to tell me nothing. But, alkenes can react with water under the proper circumstance. We can get these two things to react together. How do we do it? Well, we need a little extra help. Right now, there's no electrophile here, meaning this is mainly negative. It's not electron loving. It already has them. And the water has those free sets of electrons on that middle oxygen. This is somewhat negative, and it's not really electron loving either. And at this point, there's no really good electrophile. And remember, we have to have a nucleophile and we have to have an electrophile in order for these things to react the way that they're supposed to. And right now, I just don't have one. I only have half the story, not the full story. So we need something that we can throw into the mix to stir the pot up. Okay, in other words, here's a component that came to the bar. Here's a component that came to the bar. They're not talking to each other right now, and we need a matchmaker. We need someone to go in to say, hey, you know, this person's got a good career, got a good job, got a really good paycheck, got a house over in the Hamptons, or a beach house. Buys you anything that you want. Look, all of my analogies here deal with money. Isn't that awful? But we need a matchmaker. We need some type of persuasion to get these two things to talking to each other. What is that matchmaker? It is H+. There's your electrophile. That is electron loving. This is going to help step up the process much quicker. All right, well, what is this H+? We just don't have a bottle of H+ around, do we? No, we don't. You can't buy a bottle of H+ and put it into a flask. This is going to be some type of acid. That is what that's going to represent. It doesn't really matter what type of acid. Now, I probably don't want to use HCl and HBr and HI, do I? And the reason is because those acids, well, they actually do react with the alkenes, and they will take the spots up on those carbons if I give them a chance. So I want to stay away from those. But an acid that I could use would be something like sulfuric, H2SO4, or even phosphoric, H3PO4. Those types of acids will give me the protons that I need, but yet they do not react with them like HBr and HI and HF would, okay? So in order for us to shorthand this, and in order for us to kind of get our point across, the only thing that we do is just write down H+, and we just sometimes assume that you know what we mean by that. That means an acid, some type of acid is present, but they seem to forget that a lot of times we don't get the chance to do this in the beginning of a class. So we are very vague on what this H+ is supposed to represent. And now hopefully you know. This is an acid that comes from a bottle. And that acid, I could pick a number of different ones to use. That is why they just give me a general H+ here. They're not very specific, and they're just saying use whatever. Whatever you want to use. As long as it brings H plus into the table, then this is going to be good, and you're going to go forward. But at the same time, they also are under the assumption that we will not use HCl and HBr and HI and HF, all of the halogenated acids that were there that we've used already. All right, so once this process happens, then ding, 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 we do get a reaction that happens here. So that alkene is going to react with water. Nothing's going to happen. But if we add acid into that water and add the alkene in it, then we do get product formation that happens here. Okay, so I'm going to give you the shorthand version of this first before we talk about a mechanism. I think sometimes it's easier to see that before we do anything else. All right, so what's going to happen? If we do have acid and we want to add this water, what is actually going to happen here on this alkene? I want you to rewrite water as HOH. The reason is because we are so used to HCl and HBr and HI, and what we did is that we slapped H on first, didn't we? And then we added on the remaining part. Well, the same thing's going to happen here. We're going to slap the H on first, and then we're going to add on the remaining part. That's how I want you to look at this. So with my double bond, I told you we learn a procedure. That procedure is applied to everything, right? We're going to assume that this is a symmetrical molecule in the beginning. Well, what do you think is going to happen? This is what I hope that you would tell me. Double bond is going to break, just like it did before. Two sites of attachment open up. One there, one here. I don't know. Let me just draw those new ones in a different color so that way you can keep them separate. There we go. And then on this water molecule, we have H and we have OH. So H goes on one, OH goes on the other. Look at there. You just did it. That's all you got to do. A couple of things I want you to keep in mind. This H plus up here, this is a catalyst. We always write catalyst on the arrows. They do not take part in the product formation. They are only there to speed up the reaction. The catalyst typically take these really high humps that we've learned about before in a previous lecture module, and they will lower that hump down. And this lowers the energy of activation for these reactions. So that is the purpose of the catalyst, and that's why I call them the matchmaker. It takes this compound, the alkene, and it takes that compound, the water. It lowers the energy of activation down between these two reagents, and it allows them to react together. When that begins to happen, we start a chain reaction that will form product at that point. You also need to keep in mind that water can be written as HOH, and when you do that, you automatically can determine what atoms go on to the carbons. H goes on one side, and the remaining piece, OH, goes onto the other side. Folks, this is also a way that we make alcohols, all right? Okay, so I'm going to clear this screen off because I think that's pretty important to write down. So I'm going to clear it off, and I'm going to say we can take an alkene and can react that with water and a little bit of acid, and we will end up with alcohols as products every single time. Okay, so the alkene is the double bond, and the water is HOH. That's how I want you to view that. And the double bond will break. H goes on one side, OH goes onto the other. And there is the alcohol formation or the alcohol reaction from an alkene. Okay? So if you're comfortable with that, then this is half the story. You've already halfway there. We just need to do some examples. But before we do that, we need to look at the other half of this explanation. And the other half is the mechanism, right? We're always interested in how this mechanism takes place. You know, what happens? How does this actually go on? What are the individual steps which make this happen? Well, this is a little bit more complicated than some of the others that you've seen. So with this mechanism, we have to understand that hydrogen was there for a purpose, and we have to start there. That's where this mechanism is going to begin. If it wasn't for that hydrogen, then no reaction would happen, right? So something is happening to the hydrogen that is on top of that arrow. It's changing the role that the water is playing. All right, so water I'm going to draw just as like an OH with an H that points down like this. There is the water molecule. I know I'm drawing it a little weird, but I'm doing it to set up the mechanism because it's a little easier to draw if I do it this way. And then what we have to understand is that the acid, it's donating some proton. That's the definition of an acid. Look, lecture 2 material right there, module 2. So that acid has a proton that it's donating, and that proton is positive. And this water molecule right now, it's got 2 sets of electrons on it. It's partially negative. And it says, hey, proton, why don't you come over here, right? I got something good for you in this van. Well, I hope it doesn't do that, but the hydrogen falls for it, and it says, okay, and then it goes over, and it pairs up with this oxygen, and then oxygen runs away with it. It runs away with it. It just grabs it and goes, like Pennywise the Clown. Well, when it does this, that oxygen now, at this point, has a formal charge, doesn't it? The oxygen is typically 6 valence. And right now we have 1, 2 from the dots, 3, 4, and 5 in total. 6 minus 5. Well, 6 minus 5, this is a positive. This is the generation of the hydronium ion. It's water, but it's protonated water. And that, by definition, is called hydronium. So now, all of a sudden, the dynamic here changes. We have a double bond, and not just water, but we have protonated water, a hydronium, that's now in play. Now, this is a typical nucleophile, the alkene, and electrophile, the protonated water. So we can begin the mechanism at this point. At this point, we can start drawing the curvy arrow mechanisms. But you have to understand where the protonated water came from in the first place. And that's due to the addition of the acid. Maybe sulfuric acid gets added into the mix. That sulfuric acid releases proton. That proton goes and lays down on top of this water molecule to form hydronium. And that makes the formal charge of the oxygen positive. Now we have an electrophile and a nucleophile. We start the curvy arrow at the negative end of the double bond first, and we draw it toward the positive piece that it's going to rip off, and that is the hydrogen at this point. All right, now, once that hydrogen is ripped off, we have some electrons that are left over. And these electrons right in there, well, oxygen's electronegative. So that's probably where they're going to go. Oxygen's electron greedy. It's going to suck electrons up when it can, and even more so now because it's positively charged. And we create a carbocation in the next step. What we have done at this point is that we have broken the double bond, and we've freed up 2 sites of attachment, one of which will get the hydrogen that we have just removed from the water molecule. The next one's going to be a carbocation. It doesn't have anything going for it right now. And what we've generated is back to water, H and OH. That's what we've got. Well, good news. Carbocations don't stay around very long. They're fully positive. Carbocation. And this water molecule's polar, isn't it? This water molecule, the oxygen, well, that carries some free pairs of electrons. Those are negative. So that negative area is going to be attracted to that positive area. And I can show that in the curvy arrow mechanism. I can start my arrow here at the negative area, and I can swirl it to that carbocation. Well, when that happens, it takes care of the carbocation, but we're not yet done. This is not the final product. We're kind of in the transitional stage, aren't we? All right, so this double bond was broken to a single. Hydrogen came onto one side, and then on the other, we have just brought this entire water molecule, this OH and the hydrogen that it was carrying with it as well. Now, the problem is that oxygen, once again, finds it biting off more than it can chew. It's taken off too much. Oxygen has 6 right now, 1, 2, 3, 4, 5. This is becoming a positive charge yet again. All right, well, here's the good news. We also have more water molecule in here. That water molecule will have free sets of electrons. We just don't have one of each of these. I mean, water's going to be in there quite a bit. There's tons of those molecules. Well, this oxygen that was on the incoming water has put itself into a predicament that it needs to fix a problem. And that problem is that it needs to get rid of something. It needs to get rid of maybe that hydrogen that's tagging along. It wants to kick it to the curb. And we have another oxygen from another water molecule that is lingering around and saying, well, you know, I could give it a shot. I could see what I could do. So we can draw another part of the curvy arrow mechanism. Another water molecule comes into the picture. And that water molecule, with its negative source, will look at that hydrogen and say, come on, come with me. And pop, off it goes. And then this hydrogen says, whatever, oxygen, you keep these electrons. You can have them. I don't want them anymore. And, well, there it goes. That's where those electrons end up going. So what we have now generated is the final product. We have a double bonded carbon that has been broken. Hydrogen has went on one side. Oxygen and a hydrogen has went on the other to form the alcohol. And we've generated H3O+, which really is H+, that regenerates our catalyst. And that is why, by definition, it is called a catalyst. It should not get used up in the reaction. So it's regenerating itself toward the end after it stimulates this chain of reactions to go forward. Now, I want to take just a brief moment and review all of this awful stuff that we've just talked about. Okay? Baby steps. That's what we're doing. Baby steps. I have an alkene. That alkene does not react with water. No reaction is going to happen. But if I throw acid into the pitcher, the acid will protonate the water. And this forms the hydronium ion. That's what we call that. A positively charged H3O+. That is what this is, H3O+. So if I do that, the alkene negative bond is attracted to one of the hydrogens that's in that hydronium. And it pulls that hydrogen off and it attaches it to the molecule. That frees up a carbocation. Well, if I pull the hydrogen off, we're left off with just plain old simple water at this point. But that's okay, because this is a positive and that water carries negative. There's an electron-dense core around that oxygen. So these two things attract, and the whole water molecule gets attached first. In the mechanism, that's exactly what happens. When that water molecule attaches, it realizes that it's too many bonds, and it's got to get rid of one of them. So another water molecule, this is number 2, another water molecule is lingering around, swimming in my flask, and it sees this formation happen, and that water molecule is negative, and this is basically positive. So we do get an attraction, and just like before, that water looks at that hydrogen and pulls it off. That makes this OH group very happy at this point. It now becomes neutral. That then regenerates H3O+, which is the hydronium that I started with in the very beginning. Folks, that is the mechanism of the addition of water to an alkane or alkene, all right? So the addition of water to an alkene makes an alcohol. This is a curvy arrow mechanism that's more than one step. But folks, it basically describes how we can simply say we take a double bond, we break it, and we add H on one side and OH on the other. What you're seeing on the screen, is the justification of why that happens. So there's two different things here that will go on, all right? The first one that you might see, those questions will be mechanism based. They want to test your knowledge. Do you really understand what happens in the mechanism of a reaction? So those questions will target specific steps that we have just drawn out on a sheet of paper a few minutes ago. The other ones are just simply going to be reaction based. All right, this is the reaction. What kind of products are you going to form from that? Those are the easy ones because that's where we say double bond breaks, H goes on one side, OH goes on the other side. I mean, that's what that is all about. So two different versions of a question that you might see in Blackboard or that you might see on an upcoming test that concerns this material. Another thing I would like to introduce to you is that this reaction with water, with H2O and H+, we do have a special term for this. This is called hydration. It's a hydration reaction. So this is an alkene reacting with water under the appropriate conditions, H+. This is a hydration by definition. That's what we call that. So we can say it reacts with water and acid, or we can say it undergoes a hydration reaction. And now you know what the word hydration is going to stand for. It is the water that's associated with the acid-water addition to a double bonded molecule. And we always get alcohols as the products from these reactions in the very beginning. So now let's take a break from the mechanism and let's look at just some example problems that say, what are the products from these reactions? So the question is going to say, give the major product obtained from the acid catalyzed hydration of each of the following. Okay, that sounds real fancy, doesn't it? Acid catalyzed hydration. All right, so hydration we know is water, H2O, and acid catalyzed means it does include the H+. However the H+ comes, it includes the H+. There's the acid catalyzed part. So this is how we solve these problems. No mechanism is worried with. No mechanism is needed. And you're going to see these go much quicker, I hope, and much better. So that mechanism basically described the way that we can answer the problems the way that we're getting ready to answer them. And for A, I look at this and say, double bond breaks. Two sides of attachment open up. H from the, let's just say, water molecule plays with other H's. That sounds familiar, doesn't it? So it's forced to go here. CH3 to the right-hand side. That's where most H's are. And then the other side gets the OH. There you go. That's it. And I hope that you just looked at this example and said, that's all that they wanted? Yeah, it's all that they wanted. It's all that I would want if I asked that type of question as well. It's all that Blackboard would want if it asked for that type of question. That's it. It's just a confirmation stage where you can prove to yourself that you know what water does on an alkane. Alkene. Sorry, I keep saying that. Alkene. What's wrong with me today? B. I get a ring structure. It don't matter. Who cares? They're trying to tell me that they're trying to trick me. But you know what? This process happens the same way. So this ring structure has a double bond. Guess what? Double bond breaks. Ding, there you go. Two sides of attachment open up there and there. There's no difference in these carbons or this molecule. One carbon's just like the other, so who cares what goes on it? H goes on one side, OH goes on to the other. There you go. There's the product for B. That's all we do. We move on to the next one. Yes, folks, it's that easy. You are now predicting the products of an alkene with a little bit of water and acid. That's all there is to this. That's all that there should be to this. It shouldn't be more complicated, but it will be slightly more complicated toward the end. But again, we're just getting our feet wet. So let's look at part C. Part C, we do the same thing. We break the double bond. There we go. Two sides of attachment open up there and there. H plays with other H's. So we look at this and say, well, wait a minute. H, there's one of them to the left. H, there's one of them to the right. So according to hydrogen, it doesn't really matter which one of these it likes. Now this is not regioselective anymore. Now we're going to get a mixture of products, and that's okay. Sometimes this happens. Not a big deal. So up here, I'm just going to write both choices out. That way you'll see both of them. So 1, 2, 3, 4 carbons. CH3, CH2, CH2, CH, this is where my double bond was, so I've got a side of attachment that opens up there. CH and CH3. And I've got a side of attachment that opens up here. All right, so hydrogen plays with the one on the left, which means that the OH will go to the one on the right. Okay, so there's one choice. I could have drawn it that way. That's not wrong. But let's do the other one as well, because I know that there is no difference as far as hydrogen's concerned with either one of these choices. So I'm going to have to do that one as well. All right, so CH3, CH2, CH2, CH, that's where my double bond was, so open up a side of attachment, CH, open up another side of attachment, and then CH3. So if the hydrogen in this round goes to the right-hand side, my OH will go to the left-hand side. All right, so there we go. There's two different choices. Are they two different ones? We'll name them. Naming them will help you determine that. Well, if I wanted to name this, I'm just going to simplify this down a little bit. This CH with that hydrogen on it like that, I'm just going to write this as a CH2. All right, that will help me clean that up a little bit so I don't get confused thinking that that's an attachment. The same thing happens here. This CH with an H on it, this is a CH2 now. So I'll go back and I'll just clean that up as well. And now if I want to go and name each one of these, I can. This alcohol group, this is on spot number 2. There's 1, 2, 3, 4, 5, and 6. So this is a 2-hexanol. Okay, and then if I look at this one, this OH group, well, if I number from the left, that gets a 4. If I number from the right, that gets a 3. So 3 is a lower number. So this is a 3-hexanol. And folks, either one of these are going to be okay. The carbon to the left has 1 hydrogen. The carbon to the right has 1 hydrogen. There's no difference in the carbocations that get formed in this reaction. Sometimes this reaction will go forward and make 2-hexanol. Sometimes it will go forward and it will make 3-hexanol. And I don't really have any control of any of it at this point. I just got to let both happen. So this is not regioselective, and because of that, both of these will exist. If you look at the types of OHs that are produced, this OH group is attached to a carbon that's on 2 others. So this is a secondary alcohol. And then if you look at this one, this OH group is attached to a carbon that's attached to 2 others. Therefore, this also is a secondary alcohol. So I can't really determine which is the major one at this point. I'm just going to have to say both can exist, because this is not regioselective. All right? Now for D. For D, I get another double bond, so therefore I know that double bond's going to break. And then a side of attachment opens up here, and a side of attachment opens up there. Hydrogen plays with other hydrogens because we're adding water, right? HOH. So H goes on first. It looks at this carbon, and it looks to that right-handed carbon. To the left-handed carbon, it didn't have any. It had a double bond, and one to the top and one to the bottom. It already had 4, no hydrogens there. And then to the carbon on the right, it says, hey, you hang out with the same people that I do. Let's all hang out together. And then all the hydrogens just begin to gossip. There you go. Guys can do that too. All right, so CH3, and then I have a incoming OH group that goes there. Folks, there's the product for D. That's the major product out of the two. It is regioselective, just like A was and just like B was, because hydrogen had a very clear-cut decision on where it needed to go. It did have a concrete, clear as day decision to say, I'm going to go to the right-hand side, because that's where most of the hydrogens were. And that is how we determine the major products for these alcohol reactions. All right, so I'm stopping the video here. In the next one, we'll continue on with this discussion. We might get into the next type of reaction. We'll see. We'll see how far we can go, but we're on a roll. Hopefully, you're seeing a very common theme that is happening with these reactions. The question is just what goes on them. So now we know something like HCl, we split it in half. H goes on one side, the halogen goes on the other. And now we know water can do the same thing. We split it in half. H goes on one side, and OH goes on the other. What's next? You'll see when you come back.